All right, hello everyone. So this time we go over a new video, moving on through chapter 5, which is discrete probability distribution. So this time we cover the Poisson distribution. So in this case, the Poisson distribution is used to um, was used as a mathematical model in which typically there are situations like radioactive decay, how many people arrive at a certain place, the number of airplanes living or arriving at an airport, how many cars do you get to a gas station, for example, how many people arrive to a restaurant, how many students arrive to a bookstore, how many users log into through a certain website through the internet. So in other words, we're talking about the average number of um, people or airplanes, etc., depending on the situation. So what are the characteristics of the Poisson distribution? So the experiment counts the number of times an event occurs over a specific period of measurement, and in this case over a specific period of time, over a specific area or some distance. So the mean of the Poisson distribution is always the same for each interval in which it's measured. Okay, we'll see about that. And very similar to the binomial distribution, what they have in common is that the occurrences in each interval are independent, just like the number of trials for the binomial distribution were independent, so they are here as well. Okay, the formula is right here. Okay, p of x equals e to the negative lambda times lambda to the x divided by x factorial. Okay, it's a combination of factorials, where e is the number that we know from algebra 2.71, blah, 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 right? That number. And these are the only two parameters that we need. Actually, the only piece of information that we are going to need is the average number of occurrences. That is always given. All we need to know in order to answer this question, the number of occurrences that we want to know. Okay, so let's look at an example. Okay, so at a coffee shop, the number of customers who arrive per hour averages 7. Find the probability that exactly 4 customers will arrive during the next hour. Okay, let's look at one at a time. Okay, let's get pieces of information from the problem. So the number of customers who arrive per hour averages 7. That means this is lambda equals 7. Okay, so we want to know the probability for exactly 4 customers to arrive during the next hour. So let's see. So the probability P, okay, P of x equals 4. And let's write down the formula. E to the negative lambda. Okay, let me write down the formula. Times lambda to the x power over x factorial. Okay, so e to the negative 7 times 7 raised to the 4th power divided by 4 factorial. And if we use a calculator for this, we should get 0.0912. Okay, let me show you how to do it in the calculator. There's a combination of factorials, exponentials, etc. Okay, let me clear this. Let me second quit. Clear. Okay, so we are going to type in the constant e, which is seconds, e to the negatives. Be careful with the negative sign you use. Again, you don't want to get issues with the subtraction, times 7 raised to the 4th power, 1, and divide by 4, and we do the factorial symbol by going math, reaching the probe, and scroll down to the number 4. Click enter to get the factorial, and there it is. That's our answer, 0.912. Okay, let's go back to problem. Okay, what about fewer than 2? Okay, find the probability that fewer than 2 customers will arrive during the next hour. So fewer than 2 doesn't include 2. Fewer than 2 will be P of X. Less than 2, strictly less, but not equal to 2. Unless they told us 2 or less, which is totally different. So in this case, P of 0, X equals 0, plus P of X equals 1. Okay, so in this case, it will be e to the negative 7 times lambda, which is 7 to the 0 power divided by 0 factorial. And again, keep in mind that 0 factorial is 1, plus e to the negative 7 times 7 to the first power divided by 1 factorial. Okay, so what are we going to get here? Here we are going to get a very, very tiny numbers. So I'm going to calculate, punch it in the calculator. Okay, we get 0.000912 plus the quantity e to the negative 7 plus times 7 to the first. Okay, keep in mind that this is multiplication. This is also multiplication. And this will be 0.006383. Okay, I'll let you verify that using the calculator. Okay, we are going to get 0.0073. That's our probability. Okay, find the probability that either 6 or 7 or 8 customers will arrive during the next hour. So there are two different ways to denote this. Number one, probability of, and I didn't do this when I did the binomial example, 6 union 7 union 8. That's one way. Or P of 6 between 6 and 8 inclusive, which is the notation we have been using. That is the probability for x equals 6 plus the probability of x equals 7 plus the probability of x equals 8. So we're going to use the formula as well. So this will be e to the negative 7 times 7 to the 6 divided by 6 factorial plus e to the negative 7 times 7 to the 7th, 7 to the 7th divided by 7th factorial plus e to the negative 7 times 7 to the 8th power divided by 8th factorial. Okay, so let me highlight the correspondence for, so 6, that's this guy, and then 7, because there's too many 7s, so all I'm doing here is making a distinction of where each that 7 coming from. The other 7 I didn't highlight for this one is lambda, which is constant. And finally, x equals 8th. Okay, so calculating the first quantity, we get 0.149 plus 0.149, again, surprisingly it's the same number, plus 0.130. If we add these three numbers, the probability adds up to 0.4 28. Okay. All right, so I mean the formula is not as ugly as the binomial were when we look at it in the previous section. However, it's still kind of tedious to write the formula all the time, every single time. So, is there a way to do it in the calculator? Yes, there is. I'm gonna show you how to do that, but before going over the calculator stuff, let's go over the expected value and the standard deviation of the Poisson distribution. Okay, so the expected value, which is the mean, is lambda. Again, we were in this case for the Poisson distribution, we are talking about averages, right? So average means mean, which means expected value, and the standard deviation will be only the square root of lambda, of that given lambda. Okay, so and as usual, the minimal usual value x minus 2 mu minus 2 sigma, and the maximum usual value mu plus 2 sigma. Okay, for example 2, we are going to find the standard deviation and the cutoff values for unusual, the cutoffs for unusual values from example 1. Okay, so we know that sigma equals the square root of lambda, which is going to be the square root of 7, whatever that is. Okay, so the minimum cutoff will be mu minus 2 sigma, which is 7 minus 2 root of 7. And if we simplify to decimals, we get 1.71. Okay. Maximum mu plus 2 sigma equals 7 plus 2 root of 7, which simplifies to 12.29. Okay, so this will be for the cutoff values. So 1.71 unusual and 12.29 also unusual. All right, so for example, if they asked us, okay, would it be unusual to have 5 people at a coffee shop? Okay, well, 5 people is inside this region for the unusual values. All right, so for 5 we're okay, it's usual. What about, would it be unusual or usual to have 10 people? Well, 10 people are within the okay region, or within the usual region. But what about nobody? Well, that's within the unusual region. But what about 20 people? 20 people would be unusual at the coffee shop at the same time, right? So that's what we do, this minimum and maximum cutoff values to determine whether a given number would be an outlier, would it be or unusual. Okay, so let's look at another example, but in this case I'll show you how to do it using the graphing calculator. So a restaurant receives on average 3 orders per hour via Uber Eats for any given hour. Find the probability that the restaurant will receive each of the following. Okay, so let's compare and contrast these situations with, as opposed to the binomial distribution. So let's go back to the properties right here. So in this case, something it would be worth to mention and add here, there is no fixed number of trials. Just the same way we had it on the binomial distribution. So in this case, we have a fixed number of questions on the exam, a fixed number of times that we roll a die, a fixed number of times that we toss a coin. So in like 5 times in this case, they're not there. We don't have a top value. So what are we going to do the graphing calculator here? Well, so 7 orders via Uber Eats. So let me show you how to do it here. Let me clear the screen, clear the history. Oops, the button history. And we're going to be doing the same. Second, distribution, go down until you get the Poisson PDF. Okay, and click enter. And in this case, well, notice we have the letter mu right here. However, for us is lambda, which is the average, mean, average, lambda, whatever that is. Well, in this case, for us is 3. Okay. And the x value that we want to know, which is 7 orders via Uber Eats. So 7, and let's paste. Boom, 0.0216, 0.022, 0.022. So what are we going to write? Poisson PDF of 3, 5. No, not 5, 7. So we get 0.022. Okay, without doing the formula, we do it in the calculator this time. At most 5 order. Okay, the at most, at least, well, in this case, it will require cumulative distribution. In this case, just like the binomial distribution, the Poisson distribution will give us in the calculator all the cumulative values from the left. That is, if we say at most 5, it's going to give you the probability for either 0 or 1 or 2 or 3 or 4 or 5. Okay? Not the one at least. For the at least, we will have to do something else. I'll show you. So in this case, Poisson CDF of 3 and at most 5. Okay, let's go to the graphing calculator and let's clear the history. And second distribution, let's go check the Poisson CDF this time. The average is again 3. The x value will be in this case 5. Now it's going to give us the cumulative distribution probability. Okay, so 0.916, almost 1. So almost for sure that we are going to get 5. So if 3 is an average, well, 5 is not too far away from 3. So in this case, well, that's why we are getting almost a 1 as a probability to get that, right? So 0.916. Okay, at least 5 orders. Okay, so at least 5. Let me do the diagram just the same way I did it for the binomial distribution. 0, 1, 2, 3, 4, 5, 6. But in this case, when am I going to stop here? Because as opposed to the binomial distribution, for the Poisson distribution, there's no fixed number of trials, right? So this goes on forever. So we can use the Poisson distribution to determine what is the probability of having 150 orders, right? I can go on forever. No matter what you do in this case, this whole thing will add up to 1. Let me call this n, okay? This is equals to 1. But when we want to know at least 5, that is 5 or 6 or 7 or 8 or 9 or 10, blah, 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 or n, okay? We want to know that, we want to subtract this little chunk, everything, all the cumulative from 0 to 4. So Poisson CDF of 3, 4. So we are going to, in order to get this, so at least 5 orders, so P x greater than or equal 5. That is at least 5. So it's 5 or 6 or 7, 5 or more. That's another way to word it, 5 or more. It will be 1 minus Poisson CDF of 3, 4. Okay, so let's go to the graphing calculator and I'll show you a trick again. Now I will be able to do it. So in this case, you may not want to go all the way to click second bars and do all the process. So all I'm gonna do 1 minus, let me go up here, click enter, and change the 5 for a 4, and click enter, and there you go, 0.185. 0.185. And that's all it is. That's all about it. Again, okay, let me wrap up this section by mentioning again the differences between the binomial process and the Poisson process. So for the binomial process, we have a fixed number of trials, and we have as well a failure success situation. That's why it's called binomial, because it's one or the other, failure and success. Okay. And as opposed to the Poisson distribution, we only need to know the average of whatever situation we undergo. Number of people arriving to a place, number of airplanes arriving to or taking off from an airport, or number of cars arriving to a car wash or a gas station, number of students arriving to a cafeteria, the bookstore, the library. So averages in this case, okay? So those are the main differences between the Poisson and the binomial distribution. So in the next topic, we're going to go over the hypergeometric probability distribution, which is going to change the game a little bit, because for the binomial distribution and the Poisson distribution, the trials, every single trial, it's independent of the previous one. That is, the probability of doing a next trial is not going to be changing it's going to be always the same, regardless of whatever happens in the first or the second or the third or the nth trial. However, in the hypergeometric distribution, we are going to look at dependent events, in which you'll see how it's going to work. Okay, so I'll see you in that video. Okay.